Hello everyone, this is Saurabh from Edureka, and in today's session I'll be giving you a brief introduction about Hadoop. So let us move forward and have a look at the agenda for today. First, we'll understand what sort of data can be considered as big data. So there are 5 metrics on which you can do that. We'll discuss each of those in detail. Then we'll see what are the various problems with big data and how Hadoop solves those problems. Then we'll focus on Hadoop and we'll understand what exactly it is. After that, we'll focus on various components of Hadoop like HDFS. We'll have a look at the HDFS architecture and I'll show you how exactly it looks like. After that, we'll focus on yarn, how it works and its architecture. Then we'll write a simple MapReduce word count program. After that, finally, I'm going to discuss the whole Hadoop ecosystem. So I hope we all are clear with the agenda. So let's move forward and see the 5 V's of big data, or you can say the 5 matrix on which we can consider a data as big data. So these are the 5 matrix or factors on which you can consider data as big data. These are called 5 V's as well, because it starts with volume, then comes variety, velocity, value and veracity. I'll just give you a brief summary of what all things are here. So we'll start with volume. So the data that is now generated is huge in size. Earlier we were dealing with MBs of data, then came GBs, then terabytes, and now we're dealing with zettabytes of data. And there are many sources from which this huge amount of data is generated, like social media, Internet of Things, and various other factors. Then comes variety. Now in variety, we deal with different kinds of data, or you can say data which is present in different formats. So namely, we have 3 types of data: structured, unstructured, and semi-structured. So when I talk about structured data, a data which has a proper schema or present in a tabular format. You all know what is structured data. Now when I talk about semi-structured data, you can consider the example of JSON and XML files. Then comes unstructured data. For example, we have audio files, we have video files, images, all those things comes under unstructured data. Now comes velocity. Now this huge amount of data coming from various sources is getting generated at a very high pace, or you can say at a very high velocity. Then comes value. Now obviously the data that is now generated, you need to make sure it is of certain value. So whatever analytics that you perform is helping you in growing your business and getting better insights from that particular data. Then comes veracity. Now veracity is nothing but inconsistency. And obviously when you're dealing with such huge amount of data, certain data packets are bound to get lost in the process. Now with that causes inconsistency in data. So there might be certain columns or certain fields which will be empty. So you need to deal with inconsistency in data. So these are all 5 matrix on which you can consider data as big data. So let's move forward and understand what are the various problems in handling this big data. So this slide actually tells you about the various problems with big data. Let us focus on each of these one by one. The first problem is storage. Now storing this huge data in traditional systems is not possible. The reason is obvious. The storage will be limited for one system. For example, you have a server with a storage limit of 10 terabytes, but your company is growing really fast and data is exponentially increasing. Now at one point you will exhaust all the storage. So investing in huge servers is definitely not a cost-effective solution. So this is one problem, guys, that is storage. Then comes processing data which is coming from various sources, or you can say which is of different format. Since we saw the data is huge in size, but it is present in various formats as well, like structured, unstructured and semi-structured. So you not only need to store this huge data, but you also need to make sure that a system is present to store these varieties of data generated from various sources. And now comes our next problem. So we saw that the data is generated in huge amount, that too in various formats. So nowadays the hard disk capacity is increasing, but at the same time the disk transfer performance, or you can say speed, is not increasing at that rate. Let me explain you this with an example. If you have only 100 Mbps input output channel and you're processing say 1 terabytes of data, now how much time will it take? Approximately around 2.91 hours. Now 1 terabyte of data is very small nowadays. You can consider zettabytes of data. So in order to process zettabytes of data, you can imagine how much time will it take. So these are the 3 problems. First comes storage, then we have data that is generated from various sources like structured, semi-structured and unstructured data, plus the disk transfer performance, or you can say speed at which we process data. So these are 3 problems that we have discussed. So we'll move forward and understand how Hadoop provides solution to all these problems. Now basically, what is Hadoop? Hadoop is a framework that allows you to first store big data in a distributed environment so that you can process it parallelly. So as you can notice that Hadoop has 2 components. One is HDFS. Now HDFS is used for storage that allows you to store data of various formats across a cluster. Second is MapReduce. It is nothing but a processing unit of Hadoop. It allows parallel processing of data that is stored across the HDFS cluster. Now let us move forward and understand how Hadoop solved these big data problems. So the first problem was storing exponentially growing huge data sets. And that problem was solved by HDFS, that is nothing but Hadoop Distributed File System, as the data is stored in a distributed fashion. Now we'll discuss about HDFS later in the session. Then comes storing unstructured data, or you can say data which is present in various formats. Now that problem was again solved by HDFS because there is no pre-dumping schema validation. So whenever you are ingesting some data in HDFS, you don't need to define the schema for that particular data. Now the third problem was processing data faster, and that problem was solved by MapReduce by performing parallel processing. Now we'll discuss these things in detail later in the session, but I've just told you how Hadoop solves those big data problems. Now let's move forward and dig a bit deep in HDFS and understand its architecture. So HDFS is used for storage. It is nothing but Hadoop Distributed File System that allows you to store data of various formats across a cluster. So this HDFS creates an abstraction of resources. Let me simplify it for you. Similar to virtualization, you can see HDFS logically as a single unit for storing big data. But actually you are storing your data across multiple systems, or you can say in a distributed fashion. Here you have master-slave topology, so your name node is your master and you have data nodes which are your slaves. So this name node actually contains the metadata about the data which is stored in data nodes. And the actual data is stored in these data nodes. So name node contains the metadata about the data which is stored in data nodes. For example, which data block is stored in which data node, where are the replications of the data block kept, etc. Now whatever the data block that is stored in these data nodes, we need to replicate that data block and keep it in different data nodes. Let me explain it to you why. Since these data nodes are not the expensive servers, these are just the commodity hardwares. So the chances of these commodity hardwares failing is pretty high. So what happens when one of these data node fails? Then whatever the data block that is present in that particular data node will get lost. So in order to prevent that scenario, what we do, so we keep the replications of the data blocks. So whatever data block is stored in this particular data node will have replications and will also be present in other data nodes. So that if it fails, I can actually retrieve that data block from other data nodes. So that is the reason why we use replication. And by default, the replication factor is 3. That means your file gets replicated thrice. And you can configure it the way you want. Now let me tell you one very important thing. In HDFS, there is no pre-dumping schema validation. What it means, whenever you are dumping or ingesting some data into HDFS, you don't need to define a schema for that particular data. Now finally, I would like to add one thing here, guys. We have horizontal scaling instead of vertical scaling here. Now let me tell you what it is. Suppose a company that you are working for earlier was generating some amount of data, but now it has increased exponentially. So what will you do at that time? So one way of solving that problem is you can add more resources to these data nodes. But instead of that, what happens in Hadoop, you actually add more data nodes, and that is called as horizontal scaling. So instead of adding more resources to your data nodes, you're actually adding more data nodes, and that is nothing but horizontal scaling. So we'll move forward and understand HDFS in more detail. So guys, this slide basically talks about how data blocks are created in HDFS. Now let us take the example that is there in front of your screen. Suppose you have a file which is of XML format. Now when you dump this file into HDFS, there will be data blocks created, and these data blocks will be stored in various data nodes. Suppose the size of your file is around 512 MBs. Then what will happen, if we have configured HDFS in such a way that it will create 128 MBs of data blocks, then we'll have 4 data blocks created, and that will be stored across various data nodes. Now by default, the data blocks that will be created will be of 128 MB. You can configure it the way you want. This is how actually data blocks are created in HDFS. So we'll move forward and focus on various components of HDFS. Now let us discuss few functions of NameNode. It is the master daemon that maintains and manages the data nodes. It records the metadata of all the files stored in the cluster. Example, the location of the data blocks stored, the size of the files, permission, hierarchy, etc. Now basically there are 2 files associated with the metadata. First is fs_image. Now this fs_image contains the complete state of the file system namespace since the start of the name node. So whenever the name node has started, whatever the data that has been stored in that particular name node, it will create a file system image, FS image of that particular data. Then comes edit logs. Now these edit logs contains all the recent modifications made to the file system with respect to the most recent FS image. So whatever your most recent FS image is, whatever the modifications will be made on that particular FS image will be present in your edit logs. Now what happens at the same time, NameNode also has to see that whether the data nodes are active or not. So what happens that these data nodes send the heartbeats to the NameNode, and so that NameNode comes to know that these data nodes are active, or you can say alive. So these were a few functions about NameNode. Now we'll move forward and focus on data nodes. So now comes the data nodes. So these data nodes are the slave nodes in the HDFS. Unlike NameNode, data node is a commodity hardware that is non-expensive and is of not that high quality or high availability. And these data nodes stores nothing but the data blocks. And these data blocks are replicated and kept in different data nodes. The reason we know because we are using commodity hardware, so the failure rate of these hardwares is pretty high. And let me tell you guys, these data nodes perform the low-level read and write requests from the file system's client. So the client will send the request to the name node, and the data nodes will actually serve those requests, those read and write requests. So at the same time, these data nodes sends heartbeat to the name node, so that name node will know that what all data nodes are active and how its HDFS cluster looks like. So that whenever it receives a request, name node knows which data node will respond to that request. And by default, this frequency is set to 3 seconds. So after every 3 seconds, these data nodes will send the heartbeat to name node. You can configure that as well. So this is all about data node. Let us move forward and understand secondary name node. Now what is secondary name node? Apart from the two daemons that we have discussed, one is name node and data node, the secondary name node works concurrently with the primary name node as a helper daemon. Nothing but it provides help to our name node. And let me tell you guys, you don't need to get confused here. The secondary name node is not a backup name node. So it is not like when your name node fails, we can use secondary name node. It's nothing like that. It's not a backup name node. Let me explain you with the functions of secondary name node. So the secondary name node is one which constantly reads all the files and metadata from the RAM of the name node and writes it into the hard disk or a file system. Whatever the metadata that is present in the RAM of the name node, it will constantly read it and it will write it onto a hard disk or the file system. It is also responsible for combining the edit logs and FS image from the name node. So we have seen what exactly edit logs and FS image are. So this FS image contains whatever the metadata or the data that is stored in name node. We create an image of that, and that is nothing but an FS image. And edit logs, what these edit logs are, in edit logs, whatever changes you made to your name node, whatever changes or whatever addition that you made in the data in name node, you keep that in the edit logs. So it is responsible for combining both edit logs and FS image, which is nothing but checkpointing. So let us discuss that. Now this slide explains the checkpoint process. Let me explain it to you with the image that is there in front of your screen. So this is your name node. And I've told you earlier as well, name node contains an FS image. Now this FS image contains the complete state of the file system since the start of the name node. So this is the FS image. So what it contains, whatever the metadata that is stored in name node since the start of the system, it will contain that in this particular FS image. So whatever metadata that is stored in name node, it creates an FS image like this. Now what happens, suppose I make any changes in the edit log. Now let me explain you what are edit logs. Now these edit logs contains all the recent modifications made to the file system. So whatever extra metadata that you add, you do that in edit logs. Now suppose I've added some extra metadata in this edit log. Now what will happen? The secondary name node, which is present here, it will pull the previous FS image and at the same time the edit logs. It will pull that edit log, whatever changes that I've made, it is there in edit log if you can remember. And then what will happen, it will combine both of these and will create a new FS image. And this is called checkpoint. So I hope you all are clear with what is the function of secondary name node and what is checkpoint. Let us move forward and focus on one more component of Hadoop, that is YARN. So what is YARN? The full form of YARN is yet another resource negotiator. You can consider it as the brain of your Hadoop ecosystem. It performs all your processing activities by allocating resources and scheduling tasks. Now it has two major components. One is resource manager and another is node manager. The resource manager is again a main node in the processing department. Now what happens, the client sends the processing request to this resource manager and then it passes the paths of these requests to the corresponding node managers accordingly where the actual processing takes place. Now the processing takes place in these node managers. So node managers are installed on every data node. And let me add this thing, guys, it is mandatory that the node managers will be configured on the same machine where data nodes are present, because it is responsible for the execution of tasks on every single data node, because obviously your data is stored in data nodes and you need to process that data. So you need to make sure that the node manager is present on that particular system only. So this is nothing but the introduction I've given you about Yarn. Let us move forward and focus on its architecture. So guys, this is the architecture of Yarn. Now let us focus on the flow diagram that is there in front of your screen. Now over here what happens, client sends the processing request to the resource manager. And then resource manager splits this processing request into various parts and then allocates these parts to the node managers, corresponding node managers. Now these node managers have two components. One is app master and another is container. Now in the app master, actual processing happens. And this container is nothing but it provides an executing environment. So obviously this app master is one part of this container, or you can say it is present inside this container. Now this container actually monitors what all resources it is using. For example, the memory, CPU, disk network, etc. And then it sends that report to the scheduler. Now the scheduler is a part of resource manager and is responsible for partitioning the cluster resources among various queues, applications, etc. Let me give you an example. So for example, you have certain processes running in these two node managers. So once both of these processes are complete, it is the job of the scheduler to make sure that these two processes are complete, and then only it is combined. So this is how actually scheduler works. Now what happens, there is one thing called app manager. Basically, whenever an app master requires some extra resources, then it will go on and request it to the app manager, and then those resources will be allocated to the app master. So this is how the flow diagram of Yarn architecture looks like. So we'll move forward and focus on these components in much detail. So basically we'll talk about resource manager and node manager in detail in this particular slide. Now this resource manager has a part called app manager. Now let us discuss this app manager first. So app manager accepts the job submissions. So whatever process that is done in the node manager, the job of app manager is to accept those processes, to submit. So these processes will be submitted to the app manager and its job is to accept it. It negotiates to containers for executing the application specific application master and monitoring the progress. So basically it will be monitoring all the processes that are happening here, and at the same time it will negotiate to the containers for whatever resources are required for that processing. Now there's one more part called application master which is present in the node manager. This application masters are the daemons which resides on the data nodes, because obviously our node manager is present on the data nodes, we have discussed that. And at the same time it communicates to the containers for the execution of tasks on each data node. So you can see in the diagram itself that app master actually asks or requests for the resources and app manager provides that. And at the same time it also sends the node status to the app manager. So guys, we'll move forward and I'll actually show you practically how these things looks like, how our HDFS looks like, how does the NameNode UI looks like. And I've already installed Hadoop in my CentOS virtual machine. You don't need to worry about it. There will be a separate session that will teach you how to set up Hadoop cluster. This is just an introductory session about Hadoop. So we'll move forward and I'll open my CentOS virtual machine first. So this is my CentOS virtual machine where I've already installed Hadoop, and I've told you earlier as well, you don't need to worry about how to install all these things. It'll be available in your virtual machine, and there'll be a detailed session as well that will tell you how to set up Hadoop cluster. So this is where my Hadoop is installed. So when I click on /etc and I click on this Hadoop directory, I can find all the configuration files for Hadoop. Let me close this and I'll show you one more file, that is sbin. And it contains the scripts in order to start or stop a particular service. If you see the start all.sh, that will start all the services. And at the same time, if I have stop all.sh, so that will stop all the services. Let me close it once more and I'll show you one more directory, that is share. And the share directory, when I go in Hadoop, I can click on MapReduce. This will contain all the jar files that I'll import when I'm writing the MapReduce program. So you don't need to worry about it, but I'm just showing it to you. We'll discuss MapReduce later in the session. You don't need to worry about it. So I'm just showing you how it looks like. Let me close all of this, and I can also show you the web user interface of NameNode. So when I go to my browser and to this particular port, that is 5070. So over there we have an active NameNode. These are all the details about a NameNode. So it was start time, then what is the version, cluster ID, compiled, all those things. You can just go through it. It's pretty self-explanatory. Now when I go down, I can find the cluster summary as well. So the configured capacity is around this much. Then the distributed file storage use is 1.39 MB. Non-distributed file storage use is 7.45 GBs. Then the remaining capacity, percentage that is used, percentage that is remaining. So all these things are pretty self-explanatory. I'm telling it again. Plus data node usages. Then when you come down, you have live node. So we have one live node here. So when I go on and click on this, so it'll show me the live node, that is the data node, and it will show the details about that data node, right? And the number of dead nodes, I have 0. Decommissioned nodes, I have 0. Now when I go down, you can find all the details about NameNode. So you can just go through it. It's pretty self-explanatory. So now guys, this is how the Node Manager UI looks like. So what I'll do, I'll go up again and I click on this browse the file system, the whole HDFS file system. Now over here, obviously everything is happening in a distributed fashion, but you'll see it as a single unit. So over here, these are all the files that I've uploaded in my HDFS. So this is a word count problem. Similarly, these many files I've uploaded in my HDFS, the type of the file which is there, size and the replication, block size, modification, permission, owner, group, these are all self-explanatory. So this is how our HDFS looks like. So you can consider this as virtualization. It is pretty much similar to virtualization, where logically it appears as a single unit, but obviously it is present in a distributed fashion. So what I'll do, I'll actually open my terminal and I'll hit a JPS command that will show me all the daemons running in my machine. So for that, I'll go to my terminal and over here, I'll just type sudo JPS and it'll show me the daemons running on my system. Asking for password and yeah. So these are the daemons which are resource manager, job history server, node manager, data node, name node, right? Let me just clear my terminal. So we have discussed how the HDFS looks like, how the name node looks like, what is data node, all those things we have discussed now. So now we have understood how the HDFS looks like, what is name node, what are data nodes, all those things we have discussed, and I'm pretty sure you guys must be clear about it. Now what we'll do, we'll actually look at the bigger picture and we are going to compare YARN and HDFS a bit architecture wise. So for that, I'll open my slides once more. So basically what I'm telling you is these node managers are always configured on the same machine where your data nodes are present because it needs to process the data which is stored in the data node. So it makes a whole lot of sense. Now on the other hand, when we notice the YARN architecture, here we have resource manager. Now this resource manager might or might not be configured in the same machine as the name node. But again, I'm telling you the node manager should be configured in the same machine where your data nodes are present. So this diagram actually relates both HDFS and YARN. So I hope we all are clear with how both works in collaboration, or you can say how processing and storage part works together. Now MapReduce is a programming framework that allows us to perform distributed and parallel processing on large data sets, and that too in a distributed environment. So the MapReduce consists of two parts. One is the map part and another is the reduce part. Now in the map part, a block of data is read and processed to produce a key value pair. So we don't need to worry about it. We'll actually show you practically how it works. So in this map part, these key value pairs will form. Now the output of the mapper or the map job is the input to the reducer. The reducer receives these key value pairs from multiple map jobs and it aggregates those intermediate key value pairs, which is it will aggregate these intermediate key value pairs as a final output. So this is how it works. This is just a general flow diagram. We'll move forward and understand it better. So we'll take an example, suppose of a word count, right? So this is how our data looks like. So you have given this as an input. So it will be stored in 3 data blocks. So the first will be India, England, Australia, New Zealand. Similarly, New Zealand, England, Australia, India, and Australia, India, Sri Lanka, New Zealand. So these are all different data blocks. So this is called splitting. So you have split your data set in different data blocks. Now comes the mapping phase. In mapping phase, you'll actually assign a number to each of these words. For example, India 1, England 1, Australia 1, New Zealand 1. Similarly here, New Zealand 1, England 1, Australia and India 1, 1. Australia 1, India 1, Sri Lanka 1 and New Zealand 1. So this is your mapping phase. Now comes the shuffling phase. So in shuffling phase, it'll take the word and the key value pair. So what will happen, suppose if this is your key, so whatever the values that are assigned to these keys will be present like this, 1, 1, 1. Since in each line we have India, so we have 1, 1 and 1. Yeah, so what happens, this India is a key and the values that are assigned to it are 1, 1 and 1. Similarly for England we have 1, 1 because if you notice it is not there in the third line. Similarly, for Australia, we have triple ones. For New Zealand, we have triple ones, and Sri Lanka is present on only one data block, so it will be only one. Now comes the reducing phase. That is, aggregate these outputs, these intermediate key value pairs, these intermediate outputs, and sum it up to give the input. Now in this reducing phase, if you can notice, India is present thrice, so it will just write 3 here. So the key is India and value will be 3. Similarly, England is the key, value is 2, Australia is 3, New Zealand is 3, and Sri Lanka is 1. And finally, your output will look something like this, which is a final result. India 3, England 2, Australia 3, New Zealand 3, and Sri Lanka 1. Alright, fine. Guys, I would like to add one thing here. Now, if you can notice, this MapReduce makes a whole lot of sense. Let me tell you how. So we actually know that in Hadoop what happens, we send process to data, not data to process. So these mappings will happen on each node manager. So in each node manager, this mapping will happen. And then the reduce phase happens on the resource managers. And what will happen in the reduce phase, we know that it will aggregate all these outputs and will give us the final result. So you can say that the reduce part happens in the resource manager and the mapping part happens on each node managers. So the idea of distributed processing is properly explained with the help of this particular flow diagram. So over here what we are doing, we are sending the process to data, not the data to process, because this mapping process will happen on each node manager. So what I'll do, I'll open my virtual machine once again and I'm going to execute this word count MapReduce example. So this is my CentOS virtual machine again, guys. So over here the first thing that we need to do is upload a data set into my HDFS file system. And obviously in order to process something you need to have a data. So in order to upload the data set, I'll just type in here Hadoop fs-put and the path of my data set. So it is present in desktop. And the name of my data set, which is nothing but data set. And now I'm going to give the path where it should be stored. So I just want it to store in the root directory. So I just will keep it like that. And let us go ahead and execute this. So our file has been uploaded into HDFS. Now let me clear my terminal and I'll show it to you in the UI where it is present. So now if I just refresh this once more, so you can see the data set, the file that we have recently uploaded to HDFS is present here. So we have various information about it, like the type of the file, size, replication, block size, modification time, permission, owner, group, all those things. So I've shown you how to actually upload a data set in HDFS. Now when I click on this particular file, let us see what happens. So this is how it looks like. So this is the data set that we are talking about and we are going to run a MapReduce program on. So yeah, it looks pretty complex, right guys? So this is how our file looks like. So our next task is to actually create a jar file for the MapReduce program. Now how I'm going to do that? For that, let me open my Eclipse. So this is my Eclipse, guys. So over here we have a directory of word count. Let me just open it and show it to you. Now over here you can notice we have reference libraries. So what we have done, we have actually imported a couple of jars for our MapReduce program. Now when I click on the source directory, I have a default package where my entire code is written. Now in the beginning, if you notice, we have imported certain libraries which are very important. After that, we have a word count class where the logic for word count is defined. Now this word count has two parts. One is map. Over here you can see we have one class called map and it makes use of the two jar files that we have imported. Now this will actually create the key value pairs. Now the other part is reduce and it will take the input from the mapper and then it will join it. Finally, we have a main function in which we have certain configurations. And now in this main function, what we have done, we have defined certain configurations in order to understand that which class will be executed first and all those things, or you can consider it as your objects as well. Now this code, you don't need to worry about it. In the upcoming sessions, we'll have a separate webinar on MapReduce programs. So you don't need to worry about this program right now. The main thing that you need to understand is how the Hadoop framework works, right? So what I'll do now, I will convert this to a jar file. So I'll just right click on word count, click on export, convert this to a jar file. I click on next and finally click on next, and then click on finish. Now I have already one jar class of word count. So I'll just go on and replace this and it'll be there in my desktop. Now let me show it in my desktop as well. So here you can see that word count.jar is present. Now what I'll do, I'll open my terminal. Now let us run our MapReduce program. So first I'll write Hadoop because I'm running a jar file. So I'll write Hadoop jar After that, what I need to do is I need to specify the path where my jar file is present. So it is present in my desktop and the name is word count. So I'll just type in here word count.jar. Now in that jar file, I want to make use of the word count class. So I'll just type in here word count. Now finally, I need to give the path to my data set, which is present in HDFS. So it is present in root directory itself and the name is data set. After that, what I need to do is I need to give the name to my output file. So I'll just keep it as output-2, right? So let us go ahead and run this and see what happens. So you can see here, it'll first do the map phase and then it'll execute the reduce phase. So it is 0% now, map phase. So map phase is done now. It is showing 100%. Now it'll start the reduce phase. Alright, so it is also done. Now we have successfully executed the MapReduce program. Let me explain to you these logs that are created. Now over here, when I go up and I see it over here, so we have the number of bytes that are 92697. Bytes written are these many. Read operations 0, large read operations 0, write operations are also 0. Now number of bytes read are 48930. Similarly, we have a lot of other details present here. And this is our MapReduce framework. So the input records are 103, output records are 7352, output bytes are these many. So there are a lot other fields that are present here. So this is how it looks like. Now what I'm going to do, I'm going to clear my terminal and now I'm going to open my web UI to show you the output. Now when I go here and I'll go back. So over here what I need to do is I'll just reload it once and you can see that output 2 is present. If you can recall that the name that I've given to my output file is output 2. So when I go on and click over here and you can see that it is success now, and if I click on this part R, it'll give me the output. So we have anatomy word repeated once, configuration twice, configuring 13, data 13, input 6. So this is how it looks like. This is our output. Concept has been repeated 24, concepts have been repeated once, concurrency has been repeated 6 times. Similarly, for all the words that were there in my data sets, I've counted how many times they have been repeated in the data file. And I would like to add this thing, guys. Let me just open one port for you, local host, and this is basically for my job history, which is present at 19,888 port number. So this page basically explains the job history, whatever jobs that I have run, executed. The topmost one is the latest job that I've executed. So when I click on this particular job ID, it'll give me all the details, the job name, username, status, all those things will be present here, right? So this is the task type map and reduce 1.1. So the attempts of maps and reduces were successful, as you can see it over here. And the task type is map. So when I click on that, it'll show me the task like that. And I'll go back and I'll click on reduce part. So it'll show me the history of the reduce phase as well. So this is it, guys. Now what I'll do, I'll open my slides once more and we'll see some more components of Hadoop. I'll just give you a brief introduction about them. So this is the whole Hadoop ecosystem, how it looks like. So we'll start with Flume and Scoop, which are used to ingest data into the HDFS. Now HDFS, we know what it is. Now there's one more component called Yarn. We have discussed about Yarn, what it is. It is yet another resource negotiator. It has again 2 parts, node manager and resource manager, which we have discussed. Now let us focus on the other parts as well. So we have MapReduce. So we have executed a MapReduce program of word count. So we know what exactly it is. Then there are components for machine learning as well. So in Spark, we have MLlib. Similarly, we have Mahout. We have one more component called Spark, which is used for near real-time processing. Then we have certain analytics tools as well, like Hive and Pig. Now let me tell you an interesting story behind Hive. So basically, Facebook developed this Hive in order to perform analysis on the huge data set or big data. And it is pretty much similar to SQL. So because of this, they don't need to hire people who knows this Apache Hive. They can use the people who know SQL as well, because it is very, very similar. And there's one more thing called Pig, which uses Pig Latin. Apart from that, we have a component called HBase. Now this HBase is nothing but a NoSQL database on top of the HDFS, that is the file system. So this is just a general overview of the Hadoop ecosystem. So thank you and have a great day.